That probably sounds about right.
Yeah.
Yeah, because you have the thing for mathematics, context, right?
Yeah.
Did you actually do something?
Doing the decomposition.
Oh, and decomposition.
Yeah. So SymPy puts like a
That's right.
equation.
Yeah, that's right. Oh, things like
Yeah.
I need a better camera.
yeah.
Kind of sucks because I thought this room was one of the ones that had the cameras that follow you, you know, when you're lecturing. And I thought, oh, that's going to be sweet. Great. Awesome.
Yeah. The one on your phone or tablet better by a lot.
Really?
I know one of my tablets, it can take 4K video.
That might be very hard for me to do with the camera setup. I guess I would have to log in from my tablet on Zoom
Zoom app on
and then use that.
I know the iPad Pros have 4K video, so the newer iPhones do as well.
That's a good point.
Yeah.
All right.
And also, I'm very unsure about this stuff getting. I also always
Right
get the
there.
minus sign here, but I think that's just Relativity
Yeah, could be.
because
Yeah.
you have to insert the U,
That's right.
and then the for Relativity is a bit different.
That's right. That's right.
It's not
The 4 versus
symmetric
the 3.
under
That's right.
cyclic. Or it's not symmetric
That's
under
right.
cyclic.
I'd have to stare at this for a second. I haven't looked at these problems in a while. But don't fret too much. This is like, whose line is it anyway? So. Just don't make me mad.
That means he has to make one of the hosts.
Huh?
Does that mean he has to make fun of the host?
Wait a second.
That's a pretty important part of the show.
I guess that's true. How's the car?
It's fine. It wasn't something like major. It's just something that he wants to not drive 3 hours round trip on. So
I don't know.
like it can still run. It's fine running. It's just like something possibly wrong with the oil. It's either the oil is not being injected or just the gauge is wrong. So
Yeah.
but I feel like it's more the latter than the former because you would have noticed the former by now.
I expect. Yeah, I've been meaning to reply to your Slack message, but my kid is sick, and so he's been a screaming ball of anger since Sunday morning, and I've been juggling that. So I got in for meetings yesterday, but that was about all I could muster. Work through half of my email inbox, and that was it.
I also have to finally update my OS because with this the brew update finally finished, but it said a lot of things are now outdated for your OS. So now I need to worry about that. So that's today's agenda. Making sure that
So none of the changes I made should affect HTF5.
Yeah, that's
So
why I think
that's-
it's not that.
It's not me.
Right. I know.
Or your
That's why
computer.
I tried to. That's why I'm trying
You're
to
the one with
update it.
numbers, yeah.
So.
But no, I'm pretty happy with that because it's basically very, very, very unlikely that it'll ever crash again with the non-convergence in the EOS. Like for any problem, not just yours. Like I came up with a general solution, which was to protect the Newton-Raphson with a bisection. Because I was looking at, I told folks in group yesterday, I was looking at this problem and what was going on. Like I dug deep in and I was putting some debug statements and having it print out values, including the values for the derivatives. And so the Newton-Raphson works by going over here, compute the derivative, guess where the answer should be. And it was doing that, and in successive iterations, it would go over here, compute the derivative, and it was exactly equal and opposite to the other derivative. And so it was literally bouncing back and forth between the exact same 2 points and never converging. It never could convert. I put the iterations up to 1,000, and it's just exactly the same. And so the derivatives were garbage. I don't know why, but they were garbage and useless for this. And so I just protected it by a bisection. Bisection always converges, just slowly. So I felt good. Yes. I did a thing. I committed code. Wow, it's almost like I'm doing research. I have no idea how we're going to get through all of this. Oh, it's after time. I better start because I literally don't think I'm going to get through all this today. Okay, let's get started. Do you want to turn in anything? I think we nominally said if you've got stuff, you can turn it into me whenever. I would like it today, but if you don't got it with you, you want to take the end of the day.
I emailed you stuff, but
You did?
yeah.
Oh, okay, that's fine. I can print it. Steve,
I got work on that one.
good Lord, this is nice. And we have a solution set that I'm going to post. I'll go through and make sure they're right. If they're not, I'm going to send you corrections. Does anyone else want to turn theirs in already? You can wait. You can take them to the end of the day. And if you want to look at my notes again, you can feel free. You wait? Okay, that's fine. All right. Get them to me though today so I can go through them, and after I do that, I will post some form of solution at some point, so that we can all see what the right answers were. If you've got your homework, you can turn it in now, or you can give it to me later. Okay, so last time we started talking about 3+1 decomposition, and we talked about how we can project any tensor into a purely spatial part and then a part in the time direction or the normal direction. And we talked about how to get the spatial metric and then the normal vector to our curved spacetime. And then we noted that in order to evolve that forward in time, we're going to need more information, because we only have information about the curvature in sigma, the hypersurface that we are working in, the time slice that we're working in. And so there's no information about vectors that come out of that surface, right? And in order, that's the time direction, right? Out of that surface of the time direction. In order to evolve metric quantities and the gravitational field, we're going to need to know information out of that hypersurface. And so we decided that we're going to need something more than just the intrinsic curvature of that hypersurface. We're going to need something called the extrinsic curvature in that hypersurface. So let's now derive that. I'm hoping today that we'll get all the way to deriving the evolution equations as well as the constraint equations. We'll see. I've got 15 pages of notes. All right. Okay, so let's get going. Okay. Extrinsic curvature, meaning the curvature out of our hyperslice sigma. And we're going to call this, it's going to be represented by the tensor KAB. And it's going to come from projections of the gradients of the normal vector onto sigma, right? So we want to use our information that's in sigma to compute this, because we still want the 3+1 decomposition. And then with gamma AB, they form a sort of complete set that describes the laws of motion of our gravitational field. And so KAB is going to be sort of analogous to a velocity of the gravitational field, and gamma AB is sort of the position of the gravitational field if we make the analogy to classical mechanics. Right? This is position and velocity. We said that before. And so KAB we need to describe. Okay, so let's start with projection of the normal vector. Now it's going to look like this. So we remember our spatial projection operator, gamma AC, gamma BD, operating on the gradient of the normal vector in D. Okay? We're going to start by splitting this up, and from this projection of the normal vector onto my hyperspace, my hyperslice, I can define the extrinsic curvature. And I'm going to skip a few steps. You can look at my notes or look in the book for those. But using this projection of the gradient of the normal vector, I will get the extrinsic curvature. And that's going to be defined as minus gamma A, C, gamma B, D, the symmetric gradient of the normal vector, like that. This turns out, this is symmetric. The gradient of this normal vector is symmetric. And so the symmetrized part of that is just the tensor. And so we can simplify this. Gamma AC, gamma BD, grad C, ND. Right? Because of the symmetry here. So that's the general definition for our extrinsic curvature KAB. And because of this symmetry, KAB is also symmetric, and it's purely spatial, which means if I were to project this thing into the normal direction, in other words, dot it with the normal vector, it'd be 0, right? So this thing is still purely spatial. It exists in sigma, lives in sigma. Okay. So I want to draw a picture at some point. The normal vector is normalized such that, it's normalized and it varies only in direction, okay? So the magnitude of the normal vector doesn't change, but it can only change direction, right? So this basically says how much the normal vector is changing in our hyperslice. The direction of the normal vector is changing in our hyperslice. The visualization of that, switch to blue. If we draw our space-time diagram again, and I pick some hyperslice, right? Now again, I'm representing this all down in just a one spatial dimension like this. I can have my normal vector in like that, right? Or I could just represent it instead of vector notation just with an A. And if I move along this hypersurface over here, the magnitude of that can't change, but its direction changed, right? And so I've got some distance here, delta NA, almost an alpha again, right? Some change in the direction of the normal vector. And that change in the direction of the normal vector is actually going to be proportional to the extrinsic curvature, right? So how much the direction of the normal vector changes over our hypersurface is proportional to the extrinsic curvature. That should be a B, but it doesn't matter. Like that, okay? So let's see how we can derive that extrinsic curvature then, okay? So in other words, and remember, this is pointing out in the time direction. And so this really tells us how is my surface, if I evolve forward in time, how is it being deformed as I move forward in time, right? So for instance, the way I've drawn this thing would keep on bubbling out unless something changed the extrinsic curvature to make it stop doing that. Right? Thinking forward in time. Okay. So another way to think of this is to define the acceleration of the normal vector. We are going to define that as super duper confusing A sub A, which is NB, the directional gradient, the directional derivative of that normal vector, right, along itself. How much is the normal vector changing along the normal vector? All right. Using this definition, we can re-express the extrinsic curvature in the following way: gamma AC, gamma BD, NC, ND. That's our other definition over there. And then using that definition for the acceleration of the normal vector, we can expand this. And let me go ahead and do that, since I think it's probably instructive. Just expanding our definitions of the spatial metrics. I think this is a good reminder of where we were last time. That's the delta function plus the normal vector, NA, NC, normal one form, delta BD plus NB, ND upstairs, all times the gradient C and D. Simplifying a little bit, bringing this in and working the math out. Delta AC plus NA and C, bringing this gradient in here, and letting the delta function in this operate over here, we get BD times NC and D. This canceled, right? That canceled. And then minus the gradient A and B minus NA, A, B. Bringing that in again. And working that out. Okay? So using the definition that we have for the acceleration of the normal vector up here, this is sort of general expression for the extrinsic curvature of our sigma on sigma spatial slice. So the other thing that we're going to need is to relate not just how is this normal vector accelerating and how does that relate to the extrinsic curvature, but we're going to need to bring in how does the spatial metric change as well. And we're going to introduce something called a Lie derivative to do that. Back of the book has an entire appendix on Lie derivatives. I will gloss over almost all the details, but I'll flash up some summary. All right? So, the Lie derivative along the normal vector. Okay? That's going to be an important one. So we can actually express, it will turn out, the extrinsic curvature again. Well, actually, let me skip. We can come to that later. Okay. So in general, for a scalar field F, the Lie derivative is, here I'm taking the Lie derivative along some vector x, doesn't matter what it is, it's arbitrary, of F. That's going to be equal to x upstairs b, the spatial derivative d sub b of F, which in this case, since that's a scalar, this is just going to be x b partial b f. It's just a partial derivative for a scalar. For a vector, we'll call it VA, the Lie derivative along x of VA is going to be equal to x b partial b x, oh, sorry, v, that should be a v there, VA minus VB partial b xa. This is just equal to the commutator of x and b vector, all right? So this is just a commutator for vectors. And then finally, for a tensor, higher rank, well, I guess not finally, I've got actually one more on here. I'm skipping ahead of my notes. Let's do a one form first. So a downstairs vector. For a one form, Lie derivative along x of omega a is going to be equal to x b partial b omega a plus omega b partial a x b. Then finally, for a tensor, Lie derivative along x of some high rank tensor, we'll do mixed components TAB, is going to be equal to xc partial along c TAB minus TCB partial along c of x upstairs a plus TAC partial along b of xc. So this is all very formulaic, but what the Lie derivative does is it measures how much a tensor changes along some vector relative to just a coordinate transformation. So I've got some vector, I've got some tensor. I want to know how does that tensor change along this vector. You're thinking, okay, that sounds like a directional derivative, which it does. The lie derivative is different in that it measures the difference of that directional derivative relative to a simple coordinate transformation. So could I make a coordinate transform and get that same change? In other words, if, for instance, two hypersurfaces that we're interested in, foreshadowing where we're going to go with this, if two hypersurfaces in our manifold M differ only by coord transform, then the lie derivative along the normal vector of gamma AB, our spatial metric, is equal to 0. So the case here, you know, this is sort of, in other words, this is steady state. So if nothing, you know, about the physics of the system is changing, as I march forward in time along the normal vector, it's just equivalent to a coordinate transformation. Even if the coordinates are changing, that's fine. But the lie derivative is what measures that. If I've got some steady state situation. Yeah.
So if this holds for any two hypersurfaces.
Yeah. So I'm
two hypersurfaces.
any hypersurfaces, any neighboring hypersurfaces. Absolutely. Yeah. Thank you. Now, so in other words, the lie derivative is like a time derivative in our 3+1 decomposition. We're going to treat it like a time derivative. It's that thing that is going to measure how things change in that direction. Now, it's not exactly a time derivative, and we'll come to that a little later. Okay. Also, I mean, you might have discerned that because the normal vector is in the time direction, right? It's time-like, purely time-like. And so I'm taking some derivative along that normal vector. It's like a time derivative. Okay. So now let's derive this. And what we want to do is write the spatial metric in terms of the general metric and the normal vector. So let's write this down for the general case where we don't have a steady state. All right, so here we go. Lie derivative along n of gamma AB. By the definition of our spatial metric, this is going to be the lie derivative along n of the full metric plus NA in B, which is equal to 2 times the gradient symmetrized along A of the normal vector B symmetric plus NA lie derivative along N of NB plus NB, lie derivative along N A. That's just, I'm doing some chain rule there. Lie derivative obeys those chain rules. And then that's equal to 2 times all of this del nabla symmetrized A, B symmetric plus N symmetric A acceleration vector B, close parentheses, from our definitions above. And then this is equal to minus 2 KAB, which I erase. But this is from the general definition of our extrinsic curvature that I had up on the board a minute ago. Okay? So, very simply, KAB is equal to minus 1/2 the lie derivative along N of the spatial metric. So now I've related those two things. Okay? Also, so in one of these steps,
since the metric is symmetric, I can simplify this, right? Since the metric is symmetric. Gamma AB equals gamma BA. Okay. So now, next thing we need is the mean curvature. This is just the trace of the extrinsic curvature. All right, K. And so to take a trace, we use our inverse metric operating on KAB. Right? But we already said that KAB is purely spatial, right? And so this is equivalent to just using our inverse spatial metric, KAB. Has to be because K is purely spatial. So that's now minus 1/2 gamma AB, the inverse spatial metric, times the derivative, lie derivative along n of gamma AB, just replacing that there. And this is equal to minus 1/2 gamma, lie derivative along n of gamma, where I've taken the trace of the spatial metric. And that's equal to minus 1/gamma to the 1/2 times the lie derivative of gamma to the 1/2. That's just logarithmic rules and differentiation, or chain rule, really. And then finally, minus lie derivative along n of the log of gamma to 1/2. That's the logarithmic rule. Okay? Okay, so what this means, the implication of this is that gamma to the 1/2 d cubed x is the proper volume in sigma, our slice. So minus k measures the change, rate of change, in volume in this hypersurface. I should say along the normal vector. So that mean curvature is telling me how does the proper volume change in time. Make sense? All right. Armed with that, now we can start to work towards our evolution equations. We're going to start this by doing something that is purely geometry. And so some of these equations are, the first equation we're going to derive here is named after Gauss, like the Gauss. And you're going to go, well, he was before Einstein. Indeed, he was. And so we're going to just do geometry for a little while. And so bear with me. We're going to derive 3 equations, which are going to be important for determining our set of evolution and constraint equations for 3 + 1. Everybody read the chapter, right? So this is old news to you. Gauss, Codazzi, and Ricci. All right. And the main point here is that the spatial metric and the extrinsic curvature cannot be set arbitrarily. The reason being, we alluded to this last time, our hypersurfaces sigma, however we foliate the space-time, it must fit in the overall 4-dimensional space-time manifold. And they must fit. They can't overlap. They've got to obey certain principles. And so we do not have the freedom to set these 2 things arbitrarily. They're determined, they're constrained by the laws of geometry. And in order to determine this, we've got to relate, let me say this, we must relate the 3-dimensional Riemann tensor A, B, C, D to the four-dimensional Riemann tensor A, B, C, D, right? Where this is that spatial Riemann tensor. And then this is the full space-time Riemann tensor that we introduced last time. In order to do this, we're going to have to take several different projections of the full 4D Riemann tensor into the spatial direction and also the normal direction, and work with these three different types of projections. Okay. And remember from last time, this does not contain any time derivatives. It contains only spatial derivatives. And so in order to relate these two things, we're going to have to use the extrinsic curvature we just talked about in order to make this relation and these projections between these two things. Okay, as well as the derivative of the spatial curvature, extrinsic curvature. Okay, so a few generalities. For a purely spatial vector, call it VQ, all right? By definition, in sub Q, that's a G. In sub Q, VQ is equal to 0, right? By definition. The normal vector points in the time direction. So if it's purely spatial, that's got to be the case. This implies that the gradient along P of NQ, I did it again. NQ VQ, which is equal to VQ grad along P NQ plus NQ grad along P VQ. That's got to equal 0, right? So in other words, NQ grad along P of VQ is equal to minus grad Q grad P in Q. Someone should have stopped me. Just erase the top of that. Of course, we can't all of a sudden have second order differentiation. That's just the above line. Okay. Now, so we're going to need that. We're also going to need to expand the spatial derivative of a vector for this machinery. Okay. So, spatial gradient of a vector. DA/VB, let's call it. So remember, this is a projection of the full gradient into our hypersurface sigma. So we start with projection operator. P, I'm going to go Q, right? Oh. Follow your notes. All right. Grad P, VQ, because I'm working with vectors, not one forms. All right. So then this is going to be equal to gamma A P all times. Now we've got the mixed components of the metric tensor plus NQ in B all times grad P VQ. Watch me to make sure I don't make that grad to V mistake again. Gamma A P all times the gradient along P of VB minus gamma A P normal vector in B VQ grad along P of NQ all equal to gamma A P grad P VB minus gamma A P NB VQ grad, wait, hold on, I think I've skipped a line. It's a lot of lines of algebra here. That's fine. I was writing the same line twice, sorry about that. So this is the same, minus NB. Now I'm just going to move things around a little bit. VE, introducing a new index that I'm going to contract over. gamma AP, gamma EQ of grad P in Q. And then finally, gamma AP, grad P, VB, plus NB, VE, KAE, where this I've re-expressed in terms of the extrinsic curvature by the definition we had before, where KAE is equal to, by definition, gamma AP, gamma EQ, grad along P of NQ, right, just by definition. Okay. So now I've expressed a spatial gradient in terms of the extrinsic curvature. Exciting, right? Just wait. There's more. All right, so the second derivative, doing a lot of the same shenanigans, we can arrive at the following for a second spatial derivative, which I'll spare us all, myself especially, the math. Gamma AP, gamma BQ, gamma RC. So we're working with vectors, not one forms. Grad P, grad Q, VR, minus KAB, gamma CR, NP, grad along P of VR. I'm missing one term. Minus KAC, KBP, VP. I'm gonna look at that, pardon me. Okay, not for me. Got a sick kid at home. Okay. Now, we can redefine a 3D Riemann tensor. As follows. R BC upstairs, BA downstairs, times some vector VD is going to equal 2 times the spatial gradient anti-symmetrized VC. Okay. Now, using this expression for the second derivative, I can write this as 2 gamma AP gamma BQ gamma CR times the antisymmetric P double gradient Q VR minus 2 times KAB antisymmetrized gamma RC NP grad along P VR. One more term. Let's get too low. I'll write it over here. Minus 2K lower anti-symmetrized with the B here, P, VP. Right? Just plugging in the appropriate anti-symmetrization from our definition here for the second spatial derivative. But now, we can use the symmetries of the Riemann tensor to simplify this. Recall that it's a symmetric tensor, right? So this has got to be 0. Okay? So the second term on the right-hand side disappears, right here. And so we can simplify this even further by recalling that for any vector, the 4D Riemann tensor dCAB is equal to grad A, grad B, VC minus grad B, grad A, VC for the 4D Riemann tensor. This is just equal to 2 times that anti-symmetrized A, grad B, VC for the 4D Riemann tensor. So we can write this whole thing, again, using these two relationships, well, using this relationship and that symmetry, and lowering an index, dCBA VD is equal to gamma AP, gamma BQ, gamma RC, I've lowered an index now, times the 4D Riemann tensor, DRQP VD minus 2 times extrinsic curvature C anti-symmetrized A, K, B anti-symmetrized D, VD, after lowering the index. Now, VD in this case was an arbitrary vector. There was nothing special about it. And so I can divide it out. And then in the end, get a relationship for the 4D Riemann tensor that connects it to the 3D Riemann tensor. And I'm going to write that as follows. R, A, B, C, D for the 3D Riemann tensor, plus the extrinsic curvature AC, K, B, D, minus K, A, D, K, C, B. All of that then is equal to the 4D Riemann, oh, sorry, got to have some gammas in there. Gamma AP, gamma BQ, gamma CR, gamma DS, 4D Riemann tensor R, PQRS. After using some of the symmetry rules and dividing out that VD, and messing around with an index. So this connects then the 4D Riemann tensor. And look at this, right? We talked about projection. This is a projection of the 4D Riemann tensor. Right? And that's what it boils down to. So we can use that extrinsic curvature then to relate that projection that we're going to need to purely spatial stuff. Purely spatial stuff. This is Gauss's equation. And I'm going to write that over here on the board in the part where the people on TV can't see us. So, sorry, Alex. Because I'm going to leave it up. It's one of our 3 equations that we're going to need, and I'm going to reference it a few times. So I'm going to leave that up here. So R plus KABD minus KD Q gamma CR gamma DS 4D Riemann tensor PQRS. Right. Okay. So it's quadratic in the extrinsic curvature. Okay. Make sense? Onward. So that's Gauss's equation. The next one we need is codazzi. For this, we're going to project the 4D Riemann tensor with one index in the normal direction. So that's purely spatial, right? Like I projected everything into the spatial direction. But now I want one index to be in the normal direction. Different from that. Okay, this is not as involved. Okay, so we're going to start with the spatial derivative of the extrinsic curvature. So dA, K, B, C. And that's going to be equal to our projection operators, AP, gamma BQ, gamma CR of our gradient, P operating on the extrinsic curvature, QR. That's equal to minus gamma AP, gamma BQ, gamma CR operating on the, open parentheses, P gradient Q in R, the normal vector, plus the gradient P in Q A R, the acceleration of the normal vector. That's just from the definition we had before for the extrinsic curvature. Okay. But now, if I'm looking at this, recall that projections of the normal vector spatially are 0, right? The normal vector is purely spatial. So any term that involves a projector with the normal vector, like say, I don't know, this one and that, are 0, right? They've got to be 0 by definition. And so that can simplify this equation quite a bit. And what we get is, and also using the definition of the acceleration, all of this simplifies down to spatial gradient of the extrinsic curvature BC is equal to minus gamma AP, gamma BQ, gamma CR times grad P, grad Q in R plus AC K KB. And now from symmetry, recall that the symmetry of KAB gives us the following, and that's this. We'll see why this is important in a second. Antisymmetric D, K, B, symmetric, antisymmetric has got to be equal to 1/2 all times dA KBC minus dB KAC, close that. And then that's equal to minus gamma AP, gamma BQ, gamma CR, grad P, grad another GQ in R, antisymmetric. Okay? And then from the definition of the Riemann tensor, we've got the following. dB K AC minus dA KBC. All of that is equal to gamma AP, gamma BQ, gamma CR times the 4D Riemann tensor. Oops, skipped a step. And S. We got to have the normal vector in there. Now the 4D Riemann tensor R PQRS. After all that. And this is the Kodatsi equation. So I've heard stories that one of the authors of our book, Stu Shapiro, when he teaches GR, he writes with both hands. And I've started to understand why that's necessary. But I've heard from people who took the class, he'll draw figures with his left and and write out equations at the same time with this graph. I am not that fast or that skilled with my left hand. And also, who's going to hold my notes? I can't remember this stuff. I'm going to write that stuff over here again because we're going to need it. KAC minus DA is equal to our projection A, P, B, Q, C, R, and then normal vector in S, 4D Riemann tensor, P, Q, R, S. Right? So again, this is the projection with one index in the normal direction, right? As opposed to being purely spatial. Okay. So, grazie. Next. The next thing we're going to need is a projection of the 4D Riemann tensor with two indices in the normal direction. This is going to require the lie derivative, which is sort of the time derivative of the extrinsic curvature. Okay? Call this two indices in normal. All right. So start with that lie derivative along the spatial, along the normal vector of the extrinsic curvature. And this is going to be NC grad along CKAB plus 2KC symmetric with A grad B in symmetric NC. Okay? Equal to minus NC grad C grad A in B minus NC grad C in A in B. Oh, sorry, A, B. Right, that's how I got the minus sign, how I eliminated some of those terms, was to introduce the acceleration of the normal vector. A few more terms, minus 2 KC symmetric A, K, B symmetric upstairs C, minus 2 KC symmetric A, normal vector B symmetric acceleration AC upstairs. Writing out the lie derivative. Okay. Now we can use the relationship of the 4D Riemann tensor R DBAC times the normal vector ND, which we got from, well, I guess it's not one of the equations up there, but we had this before. Grad C antisymmetric, grad A close antisymmetric in B, like that. And so we can use this relationship to simplify this. And what we get there is the lie derivative along N of the extrinsic curvature KB is then equal to minus ND NC 4D Riemann tensor in D back minus NC grad A grad C of NB minus NC AB grad C in A minus N upstairs C in A in grad C AB minus 2 times K upstairs C symmetric A with K B symmetric C minus 2 times K C symmetric A and B symmetric A upstairs C. Yeah. I'll hold on and make sure I don't make a mistake. And remember, these are posted online. Pretty sure they're right. If I screw something up. Okay. A few more lines of math here. Okay, so using the definition of the acceleration of the normal vector and this relationship, n upstairs C, grad A, grad C, n B is equal to grad A, B, the gradient of the acceleration vector, minus grad along A, normal vector, grad along C, normal vector, one form. Like that, yeah. And that's going to be equal to grad A, B minus K, A, C, K, A, B minus N, A, C, K, C, B. With this, we can now simplify that expression. Lie derivative of the extrinsic curvature along the normal vector is equal to minus ND NC 4D Riemann tensor R dBAC minus grad along A of the acceleration AB minus NCNA grad along C of the acceleration vector minus acceleration A, acceleration B minus K upstairs C, B, KAC minus KCA in B, acceleration AC.
Fraction of the two Ks on the second line from the top one, those should have a second from the top of the
Listen,
middle term should from the indices of the second case. Or the two, probably that first or the second A.
wait, am I pointing at the right place?
Yeah. One of the two A's should be a C.
This one is, right?
On the second.
Oh, you think what? Oh, thank you. You know what? That's just me getting sloppy with my writing. It's right on the notes here. But that C in my notes looks very, very similar to an A. Really similar to an A. Thank you. Yeah, you're right. Okay. Cool. It will turn out that the following is true. I was going to do this derivation, but we don't have time, and I didn't finish it because of sick kids. So if I dot this lie derivative of the extrinsic curvature with the normal vector, this is 0. Therefore, the lie derivative of the extrinsic curvature is purely spatial. Okay, so this time derivative, essentially, of the extrinsic curvature, purely spatial. So we can use that. And we can use that by saying, okay, if I took this and projected it, projected both free indices into the purely spatial sigma, this side would be completely unchanged, right? So if I use the projection operator, the two gammas on this guy would be the same, purely spatial anyways. And so then I can just bring those two gammas over here and work them through, right? And in other words, what you would get, I'm just going to do the following to illustrate that. And I think I'm going to skip these steps because it would be very long. So I would project those two free indices using our projection operators, A, B, and that one's going to be a Q, R, right? And if I did that, I'd only end up with gammas on this side. This would be unchanged. Working that out, what that would lead to is the following. And the working of it out is in my handwritten notes. But we can skip that for now. All of this will come to lie derivative along n of KAB is equal to minus ND NC gamma A Q gamma B R of the 4D Riemann tensor R DRQC minus gamma AQ gamma BR, gradient along Q of the acceleration AR, minus the acceleration AA, acceleration AP, minus, wait, that should be a B, obviously, because I've already used the projection operator to change the index, minus K, C, B, K, A, C. Like that. Right. We can simplify this even further by using the spatial derivative of the acceleration. So that's another homework problem, but I don't think I assigned it. And that will be DAAB is equal to minus AAAB plus 1 over the lapse alpha DADB of alpha. Okay? So second spatial gradient of the lapse over here, 1 over the lapse, and then the two accelerations there. Gets me the spatial gradient of the acceleration. Putting that into our expression, the Lie derivative of the extrinsic curvature, we get NC, make that a D, NC gamma A Q gamma B R, sorry, that's got to be an R. It's another spot where my handwriting got a little, I had 2 children jumping on me while writing these notes. That's my defense. I'm going to keep using that, so get used to it. DRCQ, that's got to be an R. That's got to be an R there. Minus 1 over alpha DA DB alpha minus K CB K AC. So there's our expression for the Lie derivative of the extrinsic curvature. And this is the Ricci equation. Like that. Okay. So this relates the time derivative of the extrinsic curvature to the 4D Riemann tensor. And again, it's the 4D Riemann tensor with 2 components projected into the normal direction. So put that up here with our other friends. Lie derivative along n, KAB, equal to C gamma AQ or 40 Riemann DRCQ alpha DA DB alpha minus K. Right. Now, in 15 minutes, let's derive some constraint equations. I think I can get through at least the constraints today. Might have to do the evolutions on Thursday. But that's okay. There's only 12 evolution equations. We can do that today. A little joke there about tensor math. It's really just one expression. Okay, so constraints. Not sure we'll get to the evolution. Let's start with constraints. So what we're going to do is we're going to take our three friends over here, Gauss, Codazzi, and Ricci. And we're going to use the Einstein equations to eliminate various terms. In particular, we're going to use the Einstein field equations to relate curvature quantities to physical quantities. And that's what Einstein field equations are. Curvature, Einstein tensor, physical quantities, stress energy tensor. And so we're going to use that relationship to relate our curvature quantities to physical quantities so that then we can actually do some physics with these equations. These are purely geometry equations. No physics. So let's do some physics. Okay, so starting with GAV, which is defined as the 4D Riemann tensor A, B, C, D. Oh, sorry, Ricci tensor minus 1/2 4D curvature scalar 4 metric, all equal to 8 pi stress energy tensor, right? So we're going to use these relationships with our various projections for the Riemann tensor and its constituents to link these equations with some physics. Okay, so we're going to start by contracting the Gauss equation once. All right, so I'll get my spatial metric in there to do the contraction gamma S times the 4D Riemann tensor PQRS. So there's what's doing the contracting. That's going to be equal to R BD plus K KBD, mean scalar, the mean curvature, minus KCD KCB. All right. Now, contract again. All right. So that's going to be gamma PR, gamma QS, all times the 4D Riemann tensor PQRS. That's going to be equal to, just contracting this side one more time, R plus K squared minus KAB KAB. Right. Cool. And now we can expand this left-hand side. We can expand this left-hand side. I think I got enough room here. So this, just expanding those gammas, is going to be equal to GPR plus NPNR all times GQS plus NQNS times the 4D Riemann tensor PQRS. And all of that then is equal to the 4 curvature scalar plus 2 NPNR times the 4D Riemann tensor PQRS. Oh, sorry, you contracted. It's just got to be PR, like that. And from symmetry, I've eliminated some terms from symmetry of the Riemann tensor. Okay. All right. Another relationship that we can use also, we've got the following. 2 times the normal vector n, normal vector r times the Einstein tensor g PR is going to be equal to 2 times NP NR times the 4-dimensional Ricci tensor RPR minus NP NR 4-metric PR times the 4D curvature scalar are that. That's just multiplying through with the definition of the Einstein tensor, right? 2np nr 4D Ricci tensor PR minus, I'm going to expand this now in terms of the spatial metric, np nr all times gamma PR plus np nr all times the 4D curvature scalar. Okay? Just expanding the metric in terms of the spatial metric. So that's 2np nr 4D Ricci tensor PR plus the 4D curvature scalar R, where I've eliminated terms, right? When I multiplied this through, because that times that is -1. All of that then is PR gamma QS times the 4D Riemann tensor, R PQRS, from our original relationship over there. Right? Cool. So now we can take this and put it into our contracted Gauss equation. And what we get is, first, define. All right, first we need to define our energy density. Define rho, which is going to be the total energy density as measured by a normal observer. Put that in quotes, normal observer. That means an observer that's following, whose world line is the normal vector, right? NA. They're just going with the flow. Okay? So we're going to define that as rho, and it's going to be equal to NA, NB, T, AB, the stress energy tensor. That's how we're going to define that for our 3 plus 1. Okay, so putting all that together with this definition now, what we find is that R plus K squared minus KAB is equal to 16 pi rho. So using that, sticking it into our contracted Gauss equation, and using that definition then from also using the field equations, all of this then reduces to this equation. This is the Hamiltonian constraint. And it's the first of our important constraint equations. And it is a scalar equation. Okay. Oh, let's keep that. What do you think? Should we keep that? Okay. Great. Again, seeing the derivation is important, but really, for our lives, the most important thing is the final answer. This is what we're going to have to struggle with when we actually try to solve these things. So these constraint equations, and I think I can get to the last one in the last 10 minutes here because it's not that much actually. Our initial conditions must obey them. So when we finally get to deriving the evolution equations, which I'm sure I will have to do on Thursday now, the constraints will creep their heads up in trying to set the initial conditions for any numerical calculation that we do. If you look at your book, if you've looked ahead, there's multiple chapters on initial conditions. And it's because setting up curvature, that space-time curvature and space-time setups that obeys these constraints is non-trivial. But once they're obeyed, the evolution equations will guarantee that they're always obeyed. Set it and forget it, in other words. The setting it part is kind of tricky. Okay, so now we used Gauss's equation, cool beans. Now let's use Kodotsi and get the next constraint. All right, so we're going to contract the Kodotsi equation. All right, just once, and we'll get dB k AB is minus dA k, the mean curvature, is equal to gamma A P gamma QR NS 4D Riemann tensor PQRS, right? Now let's expand the right-hand side, similar to what we've done before. Okay, so we'll get there, gamma AP gamma QR NS times the 4D Riemann tensor PQRS is equal to minus gamma AP all times G QR plus NQ NS 4D Riemann tensor QPRS, like that. And then this is equal to minus AP NS 4D Ricci tensor R PS minus gamma AP gamma, oops, no gammas, in Q, in R, in S times the 4D Riemann tensor QPRS. And due to symmetry of the Riemann tensor, we used this already. We actually used this in the previous derivation. This term is 0. Okay. All right. Then we can further use gamma AQ times gamma, oops, keep going that, times the normal vector NS GQS is equal to, I'm just going to project the Einstein tensor here, AQ NS, the 4D Ricci tensor QS minus 1/2 of gamma AQ NS GQS times the 4D curvature scalar, right? I can use that. And all of this then is equal to gamma AQ NS times the 4D Ricci tensor QS, because here that projection's got to be 0. Because, as an aside, AQ times NS GQS, which is equal to gamma AS NS, gamma AS, the spatial metric, dotted into the normal vector, right? Spatial metric times the normal vector dotted into the normal vector, it's always 0. So that second term, this guy is 0. You work that out. Okay. Okay. So now let's go to the next board. Spilling some ink today. Now, all of those things put into our contracted Kodotsi equation give us the following. Spatial gradient B, K, B, lower A, minus spatial gradient A of the mean curvature K is equal to minus gamma AQ normal vector NS Einstein tensor QS. That's it. Now let's define the momentum density. Same deal as before. This is going to be the momentum density as measured by a normal observer, world line in A, right? That's going to be SA. We're going to define that to be minus gamma A, B, N, upstairs C, T, B, C, right? Taking the appropriate components of the stress energy tensor. Plugging this into the above equation, we get spatial gradient B of K upstairs, B downstairs A, minus spatial gradient of A, the mean curvature, is equal to 8 pi momentum. Again, using the Einstein field equations coming in through here. That's where I get my 8 pi. And this is it. This is the momentum constraint. How many equations is that? Is it?
Or 3.
Why is it just 3?
Spatial.
Purely spatial, right? So it looks like 4 because our indices go from 0 to 3, but this is purely spatial, and so it has nothing to say about the time index. So it's actually 3 constraints. And so together with the constraint that I've already erased, the Hamiltonian constraint, there's 4 constraint equations. And what did we say last time when we were counting equations? How many equations associated with gauge freedom do we have? 4, right? And it's the same reason. Right? So we've got these 4 constraint equations. We didn't get to using the Ricci equation. This one, I mean, you know, by extension, you can guess where we're going. We're going to use the Ricci equation to derive evolution equations next time, not this time. But we've got our constraint equations. That's it. There's 4 of them expressed in 2 expressions, the Hamiltonian constraint and the momentum constraint. And again, you satisfy these once, and they're done. They involve only, if you look at them, I erased the Hamiltonian constraint already, but they involve only the spatial metric and its derivatives, and the extrinsic curvature and its derivatives. Spatial derivatives of that. And obeying these constraints are what allow our space-time slices, our spatial slices sigma, that's what allows them to fit correctly into the 4D manifold M, right? That's what allows us to mathematically correctly make this foliation of space-time and split the equations the way that we've done. It's kind of cool, right? That it boils down to just 4 equations and allow you to do that. Okay. Yeah. I think that's it. Questions? So the evolution equations won't take that much more. I get to draw a pretty picture next time. Okay, this was some hairy math. It actually took me a while to write up this section of notes. And I found the book to use skip steps. And I went back and tried to fill in the steps. And that took me a while, especially with sick kids jumping in. There's that excuse. Okay, any questions? Okay. Oh yeah, so before we go, I posted homework 5. It's 5 problems from this chapter of the book. Most of them deal with the short shield metric. And so a lot of the problems in the book, and I hope you're reading through them and you're reading the problems, do read the problems. A lot of the problems are show that, derive this, show that, derive this. And some of those I'm trying to do in the notes, just as we go along, as I see fit, as we have time. But I assigned some of the problems that I thought were a little more, you know, in contact with physics. I think they should be fun examples of how you then use this mathematics on in a lot of cases, the short shield metric. So those are the problems that I assigned. We'll have to work through those together. No class, so this is Tuesday, right? Today's Tuesday. So Thursday, and I'll just warn you now, there's no class next Tuesday, so a week from today. And then after that, They'll be Thursday, and then there'll be spring break. Your TOV solvers are due after spring break. And feel free to ask questions about those. I meant to sit down this morning and write one. I'm going to put myself on a clock so that I can prove to you that this is not a hard problem. See how long it takes me to write one. I'll probably embarrass myself. But it should be fun. It should be fun. I know Halbert and Steve have already at least got the polytropic version working.
Yeah, I got the same exact results as you. I'm not convinced that they're describing what the results in the book are completely correctly.
Well,
Or at
wow.
least what they're referring to is equilibrium.
So have you all been following this in the Slack channel? We are having trouble, they are having trouble reproducing one of the plots from the book. So I'm going to try it. You all try it and see what we get, and we'll have a democracy wins. How about that?
I can reproduce plots out of the result of the book. Roughly, I mean, they don't
Yeah.
have polytropic EOS
Right.
there, but my curves generally follow the same path as the other equations state they use. This one, it's the right form and the right mass values. It's just the maximum is not where it should be. And we get the same thing.
It's weird.
So I actually found a PDF of various errata for our book. And maybe I should look through there and see if they've identified any mistakes in that plot or something. It's possible. It happens.
N is slightly smaller than 1. You can almost match it exactly. But that doesn't make sense.
Right. Okay. In any case, for homeworks 1 through 4, get them to me at some point today so I can start looking at them. Don't stress too much about it. Okay, thanks everyone.
The only part of the TOV solver